Good morning, everyone. I think we are a bit ahead of time, but I do stand between you and lunch. So thank you for the invitation and the challenge to do the last talk this morning. My name is Kenneth Kwok. I come from the Social Cognitive Computing department in IHPC. Maybe a bit about myself before I start. So I'll be first to say that, Claire, I'm not a roboticist, so I feel like an outsider in this symposium. My training was in psychology because I was interested in understanding human cognition for machines. So I think of myself more as an AI person. So my talk today will be about AI. So when I was asked to give a title, I came up with this, but I realized that maybe I've given myself a big challenge because also I'm coming from outside robotics to try to answer this question. But I'll try my best. But I will come from the perspective of a program that I led for the last 5 years. So this was the Human Robot Collaborative AI program. And it was a big program involving not just A-STAR. So in A-STAR we had IHPC, I2R, and of course ARTC here. And we had also collaborators from across the different IHLs in Singapore. As you see, because the expertise we require is very wide in this, so we needed a big team to cover all the ground. Yeah, so when we started in 2018, you guys are all roboticists, most of you are roboticists here, you would be aware that robotics have made great inroads into industry, and robots were already doing a lot of amazing things, right? Lifting heavy objects, working at high speeds, doing repetitive tasks with high precision, and in dangerous and hazardous environments. So these were all very suitable use cases for industry robots, right? These were, as you note, very controlled environments. All the tasks were fixed, right? You decide ahead of time what you wanted the robot to do. Everything in the process is known. Anything unknown coming in, you have to stop the whole process, right? With the exceptions. Perception is specialized. You recognize things that you need. You detect states that you need to, but that's basically it. It's all very controlled, right? Everything's pre-programmed. More importantly, you can see from this picture, there are fences. So that means that people are not allowed when the robots are working, right, in these areas. So essentially what's happening is that factories were adapted to the limitations of robots, basically. Robots are basically quite dumb, if I may say, right? They're very good at doing certain things, but they are dangerous to be around because they don't know what they're doing sometimes, right? Or most of the time. About the same time, a new class of robots called cobots were coming into industry in a big way. So UR is the first company that sort of like sold robots, cobots in big numbers. So in 2018, they started selling like 27,000 robots. So this was an emerging trend at that time, right? And cobots are designed to work with humans, right? Instead of industry robots where humans are actually excluded. So cobots are designed to work in shared workspaces together with humans. And they're designed to work hand in hand with humans, not to replace the humans. So there is a lot of potential for cobots actually, to help humans instead of like taking over the jobs. And cobots have nice features for small companies, right? Cobots are relatively cheap. You can get one for about 50K Sing, right? As I said, it's designed to work within human workspaces, and they are space efficient. They don't need a lot of space to deploy them. More importantly, they are repurposable. What it means is that they can be easily programmed to do many things, right? You don't just buy them for one purpose and one purpose alone. So if you look at this and compare to industry robots, right, I think cobots are eminently suitable for smaller industry players, right, SMEs and so on. I think this is where this is very exciting for SMEs. The problem, however, is that cobots are still dumb, right? They lack the intelligence. So that's why Collab AI program is focusing on intelligence. But first, we make the assumption that there was this elephant in the room, right? We all know that manipulation is still a big problem, right? And in 2018, we already saw that things were happening that tells us that eventually manipulation should be solved. So we were making the assumption that this is not a problem that we're going to work on. We're going to work on the intelligence part of it, right? So our goal of this program was to achieve a fundamental shift in human-robot interaction from one where humans have to learn to work with robots inside specially designed workspaces to one where robots adapt to humans, learn about humans, and work within human workspaces. This is actually very ambitious. I think we all in this room will know. Our vision is to allow a cobot to join a human team without special setup, just like a human teammate would if the human was to join a team, right? So we're not exactly replacing humans. We are working with the humans in the team, but the robot will come in and join the human just like a team. What do we mean by this, right? Okay, maybe I take the while to explain what collaboration robots is about. So in the literature, we have 5 levels of collaboration, starting with the bottom left where we are talking about completely no collaboration, right? This is where, in the traditional way, robots are fenced off from humans, right? You do not share the workspace. Moving up, you have coexistence, where you start to share workspaces, but you are separate still. You do not have a fence, but your workspace is clearly demarcated. You do not intrude into the robot's space, right? And then sequential collaboration is where you can actually start to actually share the workspace, but you don't share it at the same time. You do it sequentially, right? That's sequential collaboration. Now, moving to the first top 2, this is where we're talking about true collaboration, moving towards true collaboration where you actually can work together within the same space at the same time, but maybe not on the same thing first, right? You could work on different parts of a problem, so that's cooperation. But eventually, true collaboration involves very, what's the word? Very very close collaboration where you work on the same thing and you basically respond to one another. So it's responsive collaboration. Okay, so oops, I moved back. Here we go. Yeah. So most of the collaboration still exists in the coexistence and the sequential realm because of safety concerns, as I'll mention later. But the whole idea of Collab AI is to really move towards eventually real responsive collaboration, working together as would a human teammate, right? Our use case initially was to have a gearbox inspection troubleshooting rework use case. And you can see in that video that the equipment we're handling is quite heavy. You have to wear gloves, right? And to disassemble this, you actually need more than one person to do it properly because the parts are, have to be meshed together, and one person handling many parts would be difficult, right? So the idea we had was, okay, this is human-robot teaming. If I can ask you to click the first, yeah. So the typical task.
Populate casing base.
I'll let you watch it first. Yeah. So you can see that you have to mesh the parts together, and you need more than one person to do it properly.
Populate the casing base complete.
Yeah. Before you click the second video, I'll just say that this is a typical task for a human joining a team, right? We have to teach the human, or we have to tell the human how to do a task. We don't program the human. So this is the typical task that we use for this whole program, where we are trying to program robots using demonstration, right? So if you look at the next video, what happens is that one of the roles is now taken by the robot. And we actually teach the robot and extract the information in terms of the task graph you see on the left-hand side. And the robot then knows what to do at the right time by following the procedures. More on the details in the next few slides. Okay, thank you. I can click this one, yeah. Okay, I'll talk about a few things that we needed to do in the program to achieve these kinds of collaboration. So first, we need to have what we call grounded perception. So this is related to vision, the last talk. We wanted the robot to be able to use not just vision, but speech and touch as well, to understand the human when the human is demonstrating the task, right? So we had this thing called instructions expressed, so verbal instructions, right? Or assemble the sub-assemblies, for example. Then we have things that the robots can observe visually. These we call them task operations, right? You have to recognize the person who's picking up this part and recognize the part as well. So this is what we need to do. Recognize the verbal instructions, the visual operations, and then relate it to the task structure. We did not initially build this by learning. We actually had the task structure defined first, but then we had to actually learn to ground the observations to the structure to understand what's going on. We also had work on haptics. So this is where we use touch to identify textures. So we have the state-of-the-art achieved here, being able to recognize textures using just 1.5 seconds of contact, just like humans would, right? And you get 98% accuracy for 23 textures. So that is grounding your perception. Next, we wanted the interaction to be natural. So at that time, 2018, we didn't have LLMs. Okay, today everybody is saying no big deal, right? We just talk to the, talk to the AI. But we had to do it the hard way, the traditional way at that time. So we wanted dialogue to be more interactive. So we were pushing the envelope in terms of whether the robot could proactively seek information. So you understand the task, you understand what you don't understand, and you ask for information. Right, so this is related to grounding your perception also. We also had to solve all these problems that had to do with real life. How do I do this? Oops. Here we go. Yeah. These are real world deployment issues. So we had to work on things like being able to recognize the Singaporean speech, far few microphones that were not worn by the human. Yeah. And also working in very noisy environments. So we did work in all this. Then, of course, everything comes together. You have to learn the task, right? So you have to understand what a human is doing. And so we developed ways where we had to make the learning more robust, able to generalize. So we split up the learning into atomic parts so that we can recompose whatever we learn from the human. And also the learning has to be done at the fine-grained level. We can't just recognize the actions. We have to actually recognize the states and also different relationship between the actions. So we develop representations for these. And at a lower level, we have to learn the skills. So what we did was to work on things like visually guided learning, visual servos. This allows the robot to perform the low-level skills in a very adaptive way instead of having everything by programming. Right? And finally, we put all this together in what we call a cognitive architecture. So it's well and good to be able to do individual components, but we needed an architecture to sit on top of ROS. Right? So this gives us the generalizability. We're able to learn tasks represented in the task structure at a high level, and then this allows the cognitive architecture to do the reasoning, planning, again at a high level, and then work with ROS to do the control. Okay, so this is inspired by the human cognitive system. So the human system has got a brain, has got a spinal cord. The brain works at a high level, at a slower rate. The spinal cord works at a higher rate at the with the hardware, so to speak, your muscles and so on. So we have this idea of putting cognitive architecture on top of ROS, and then we had a tight integration that allows ROS to control the robots with the necessary drivers and so on for different robots. Right? So at the end of this, we had the gearbox task, which was our sort of like a toy task, but then we worked on actual real cases with industry. So the first one I'll show you is by some work we did with P&G in product testing. So what they need to do is they have these bottles, right? They have to fill different liquids in there, and then they have to make sure that the bottles are performing what the able to survive the use by consumers. So they have different testings that they do with the bottle. And every time they had a program, a different bottle, they had the bottleneck was the robot programmer. So we were trying to help them do the task without having to rely on a robot programmer, but instead the technician can actually just demonstrate to the robot. The second use case involves the visually guided manipulation that we came up with, and it was used by a company called Ariantech in urban farming. So I'll let you watch the videos. So this was a framework where we had the interface and then the to learn from the human. Two modes. One was.
This is the area where the empty.
So this is a demonstration using a fixed camera. So the first mode is using a fixed camera.
Start the demonstration. Demonstration completed.
So each step is demonstrated, right? And the robot recognizes what the actions were, like pick up the bottle, from which part, put it into on a scale. And then there's a second mode where the P&G requested that maybe we can do it using normal camera, handphone cameras. So we developed a second application where we use a handphone camera, and then we had an interface where you can using just an interface to help to sequence the programming. So this then gets translated into an actual program by our architecture. And this then is interfaced with ROS and controls the robot. So here the robot picks up the bottle, puts it on a weighing scale, notes the weight, right? That's the filling. There's a tube there that actually does the filling. And then after completing that, it will pick up the bottle again and place it at another location. And all these locations were specified during the teaching. So this is programming by demonstration. The next use case was visually guided root cutting. So the novelty here is that they are trying to harvest the whole plant. So if you go to supermarkets, a lot of the automated harvesting is actually at the leaf. They cut everything, you get loose leaves. So this company wanted the whole plant. Actually, this work was done here at ARTC downstairs, in close collaboration with our partners here. Okay, I think you get the idea. So while all this was happening, okay, maybe just to summarize a bit about our program. So the whole idea, as I said, the canonical task we were aiming at is programming by demonstration. And so we had to develop all the multimodal learning abilities to understand the human demonstration. We had the natural dialogue interaction, like you heard earlier in the video. And then we had to develop robust manipulation using multimodal feedback to do the control. And on top of all that, we had the reusable architecture for high-level control and interaction. So all this enables cobalt programming through human demonstration and instruction and so on. Yeah. There is actually a website for this. If you go and Google search Human Robot Collaborate AI, you'll find a webpage for more information. So while all this was going on, in recent years, we were kind of disrupted by things that were happening out in the AI actually. So everybody here is familiar with ChatGPT. So that's an example of what we call LLMs, large language models. To be honest, as an AI person, I was amazed at how we got here in the last 10 years. If you asked me 10 years ago whether we will achieve this, I'd say it's impossible. But it's amazing what deep learning can do. So this is really, and the scary thing is we don't really know how it does it. Okay, so, right, so that's LLMs. And what you can, and the other part to this is now people are building VLMs, vision language models. So the large foundation models now include visual information together with language. And what that gives us is the ability to understand speech and gestures. So gestures in terms of vision, right? Out of the box, so in AI we call it zero shot. Out of the box, you can understand the human speech without all the fine tuning and training. Interestingly, it gives us common sense as well. So a lot of language encapsulates knowledge about the world, which is common sense, right? And this was a big problem for AI until now, right? And then it also allows us out of the box to recognize objects. So in our work, we had to specially train all the object recognition. So hopefully with advances in VLM, we can do this zero shot, right? It gives us more flexibility. And then at a larger level, you have to understand the scene. So scene understanding, recognize objects, how they're placed, the relationships, and so on. So this is the power of LLMs and VLMs. At the same time, more recently, you see a lot of impressive demonstrations of humanoid robots. Again, these are happening very fast, right? In like 2-3 years, we've gone from the Atlas robot, which is kind of big, clunky, and you know, a bit scary, to things that you might now you see in the videos later. You might actually have a humanoid robot coming into your living room. You can imagine that happening. Okay. What the advances here are in terms of ability to move in human spaces, locomotion, handle the complexity of human spaces, the strength and dexterity in the hands to be able to manipulate objects, carry heavier loads. And what's interesting to me especially is the bio-inspired actuators. You notice that a lot of the robots that are either through mechatronics or through, you know, even the electrically driven actuators are kind of still very stiff, right? There's work now that's done that mimics the human tendons and things like that. So this gives you a more human-like way of moving, right? And of course, natural interaction through web language, right? That's something that we're all familiar with today. So first, I'll give you a video on voice control. So this is work that we did after the program ended. We integrated LLMs into our work. And you can actually try this yourself upstairs. We have a demo upstairs. We call it the claw machine. I'll start.
Pick up a red ball at the corner.
Sure. Let's proceed to pick up a red ball at the corner for you. Is this the ball you want?
Okay, pick it up.
Great. Proceeding to pick up the red ball at the corner for you.
Pick up any ball that you like.
I'm sorry, but I can only pick up specific objects based on the request. If you have a particular ball in mind or any other specific request, feel free to let me know.
Okay, pick up one of the purple balls that is not next to a blue ball.
Sure, let's go ahead and pick up one of the purple balls that is not next to a blue ball for you.
I don't know. That's right next to the ball.
Is this the ball you want?
No, it's right next to a blue ball. No, let's start again.
Got it. Let's start fresh.
Pick up one of the red balls that is next to a blue ball.
Sure, let's go ahead and pick up one of the red balls that is next to a blue ball for you.
Yeah, I'll stop it there. I think you get the idea. So you notice the interaction is natural and it's really zero shot. All this was never rehearsed, right? You just tell it to do what it does, and the instructions are quite complex. It doesn't always get it right, as you saw, so it's not perfect. So that's something that you need to work on if you want to deploy it in mission-critical tasks. But the potential is there. So it makes it a little easier to string together. So there are tools out there, right? What we were using were things like ChatGPT, grounding Dino to recognize the objects, ground the objects. And then there's LangChain that sort of chains everything. So the tools are out there. You can actually put this all together very quickly. I think we did that in less than a month, I think, yeah. So large potential in terms of the natural language interaction. The other thing I pointed out was the advances in human robotics. Some of you may have seen this already, but I'll play it anyway for those who, oops. You may help me to click that, if you don't mind, to play the video. So this is a promo video from Tesla. So it features some of the advances that this was 2023. I think lately they have even more advances. So someone said this robot walks like one of the US presidents. Or ex-president. So the dexterity, the movements are actually quite amazing. To me, as a non-roboticist, I'm quite impressed. But how much of this is actually autonomous? There's some questions about this still. All these videos are very sleek. You can go and look for all these other humanoid robots that are on the right as well. They all have very sleek promotional videos. In fact, there was a bit of a buzz lately because Tesla had an event and they showcased these at a live event, right? The backstory is that Elon Musk told the team, I think a week before he wanted them to deploy. So a lot of the actual demonstrations there were teleoperated behind the scene. So it created a bit of a controversy after that but the team did not have a lot of time, so they had 1 week they had to deploy, and everything looked very impressive, but quite a lot of it was teleoperated. So we don't really know the intelligence, how good it is right now, but in terms of the mechanical parts, the advances in terms of form factor, I think it's quite impressive. So the potential is there. Humanoid form factor is especially suited for human environments because it's made for humans. You need to open drawers, you need to click buttons, you need to handle messy floor areas so the wheels don't work in this area, right? In such environments. So humanoids are good for that, but there are issues as well, right? So I will next talk about a few, what I see as challenges for attaining real human-robot collaboration. The first, of course, is safety. So for cobots, this has been handled in terms of the separation of space, like I mentioned earlier. In some situations, you can actually have sensors that detect when a human is close enough, then you have safety-rated stops. Or you have ways that you control the speed and the power of the robot adaptively through sensing. So the safety can be controlled to some extent using sensors. Even so, my understanding is that currently a lot of industry is still finicky about this. They're not so confident because you can still have accidents. But in a sense, it's a bit like human, right? Human and human work together. It's never 100% safe. Sometimes a human can injure another human also. But that's the thing. Safety is still something that is top of mind, and it may be a limiting factor. But even more of a problem is humanoids when they are in very open-ended tasks in your living room, for example. Do you trust it? So safety is a big concern. How we get there, not clear, right? So this is a big, major challenge. Okay. And then robust manipulation remains a challenge, right? Although we have made a lot of improvements in this area, to really be adaptive in motion planning, so you have robots working next to each other, you may impede, your action planning has to take in consideration other team members, could be humans even, right? Handling what they call soft materials, right? Deformable materials is still a challenge for robots. Then precise manipulation. So we have one of the tasks right now is for electronics testing, replace the human in testing products by inserting, like your USB cables in. Not easy for robots still today. So I think this term, physical AI, was coined by my friend Remanufacturing from Intrinsic. So this, I think this is the next frontier for AI. So we have a lot of improvements in LLMs, VLMs with perception. Now it's the action part where you have to actually physically interact with the world. So this is the next challenge for AI actually. And finally, of course, we are working with humans. So there are a lot of things that we take for granted when humans and humans work together. Something called theory of mind in psychology means you have to sort of understand what the other person understands. You have a theory of what the person's mind is, right? So I need to know what your assumptions are in order to be able to work with you in the right way to satisfy your needs, right? You need to understand the human intentions, the needs. There are certain norms when you talk about social spaces. So in fact, one of the projects that we're going to work with ARTC on is in giving robots and humans a certain protocol to work together in shared spaces. So this is still an open problem. Otherwise, you have an issue of like the robot controlling the lift and then the humans get shocked, like how come the lift is moving by itself, 7 months? Okay. And then social common sense. So there are a lot of things that we assume that the other person knows, right? You don't do certain things. So if say elderly person, you don't overwork them, treat them with respect. Social common sense. is something that we take for granted. So there are a lot of things that human-human interactions have to be carried over into human-robot interactions if you want to really do true collaborations. So I think this is my last slide. So are we there yet? I started with these questions. I'm not sure if I've done it justice, but this is what I think would be my conclusions. So I hope I showed you that AI and robotics are really advancing quite rapidly, in our own work, as well as in the general AI area, where you have these generative AI models and humanoid robotics. Yet, as I showed you, there are still major challenges that may stand in the way of true human-robot collaboration, right? So I guess my answer to that is we're not quite there yet, but it's we've done quite a lot at this point. And what do I think will happen in the next, next 10 years? I think cobots working in work cells for SMEs are something that I'm really excited myself about. We're trying to make that happen. In Singapore, I don't think the take-up of cobots is still very low, right? I think there's a lot of potential there. So this is the first target for my team. We're trying to see how we can introduce cobots with intelligence to SMEs, right? Humanoids in factories could come about, right? But not in your homes yet, because as I said, safety is the main factor. Are you comfortable with having the humanoid in your home at the moment? Even though it costs like 20,000, that's what Elon Musk is targeting. So he can sell his robot at 20,000, and he expects billions to be sold very soon. Well, that's his vision. So I'm not sure. So the robots in homes part, I think, will be the far future, a question mark. Right. So thank you for your attention. I'm not sure where the time.
We still have time for Q&A. If anyone wants to ask Dr. Kwok any question.
Hi, my name is Ravi. I'm from JM Westech. So, in a way, I don't have a robotic background. I'm basically from life sciences. But I've just stepped into Vision, and this is my first, symposium for robotics. So it's quite interesting. Thank you for your talk, quite insightful. I had a couple of naive questions, rather. So you bring common sense and you talk about cobots, right? So what's your perspective of, because common sense is also among humans, it's quite subjective, right? What you think is common sense to you might not be common sense to somebody else. So I'm quite intrigued on how that problem can be solved. Any views that you would like to share about that?
Yeah, I think that actually personally, that's one of the areas I am very interested in also in common sense. In fact, my previous work, we were trying to build common sense knowledge bases, which now actually with LMs, we don't really need that. It's sort of disrupted that work. So to answer the question, I think what common sense I'm referring to LMs now because that's where we think this best tool that we have right now, right? That you don't have to build; it's already there for you. The danger is it may actually do things that or tell you things that are common sense to some extent that from its own learning, from its own reading of the internet and whatever material it has. It's learned certain general things. So these general things can be common sense in a sense. But it may do things, the AI may do things that actually violate social norms sometimes, or it may violate safety, for example. So these are concerns. So I think it gives us maybe 60–70% of the solution because in many things that you do in the real world, the common sense in LLMs are applicable and okay. It solves a lot of problems that otherwise we have no way of solving previously. But for the mission critical things, we are doing things like putting knowledge graphs on top of the LLM. So knowledge graphs are structured knowledge that are verifiable, and we know we can actually say these things are safe, right? So we sort of put a box around the LLM, constrain it, use it as a resource, but we don't allow it to control everything. So that's one approach that we're taking for common sense. Yes.
Hello, I'm Jim from ARTC, working on robotic systems. Thank you for the great talk. So within my team, we have worked on cobots a lot and even deployed some in industry. So one of the concerns I hear from industry often is cobot-based systems are often quite slow. So the question is efficiency, throughput, especially for manufacturing, for industry. So how, when you have a cobot-based or a human-robot collaboration systems deployed, how can we ensure that they are also efficient and can meet the throughput requirements? How can, what do you think about it? Thank you.
Yeah, it's the same question that we get asked all the time also. So I think that the answer would be in adaptation, right? It has to be not one answer to everything. Robots are not necessarily slow by nature. You can make it go as fast as you want it, right? That within its own design, right? The reason it's slow is because of the safety aspects. So if we can have safety systems where when a human is involved, then it's slow. When a human is not in the loop, it can actually speed up and do things much faster. So one of the things that we're doing is we leverage a human in the teaching part, or the part where the human needs to do, and then the things that can be automated, the robot can then do by itself maybe, and that can be unrestricted in terms of speed and even the force that it can use. So I think intelligent adaptive deployment could be the answer to that. Question or comment?
Hello, morning, doctor. I'm Zaf from SSR, Malaysia. I was thinking about the ethics. Who would be the major regulating bodies for doing the ethics of the robotic? Since you're talking about physical interaction, human and the robots coexist with each other.
I guess I'm not the best person to answer this. There must be organizations in robotics that handle these. I think I understand in Europe, the European Commission itself has certain regulations about this. So maybe someone knows and can help me with the answer. Who controls ethics in the robotics? I mean, there must be some technical committee or something that governs these things like ISO maybe.
Yeah, because you're talking about the theory of mind, so that we're giving consciousness to the robot itself. No?
Not quite consciousness. We give it ability to make certain. So it's an idea about what beliefs the robot has about the other person, right? So yeah.
Yeah, understood. Yeah, thank you.
Right. So you can also ask our exhibit question. I'll play this. Oh, sorry, can you click that? Yeah. So tell me why there are so many balls on the table.
It seems like the balls are having a ball of the time on the table. Maybe they're having a meeting, planning a party, or just enjoying the spotlight. If you have any other questions or requests, feel free to let me know.
Yeah, so go have fun with the exhibit upstairs later. Right. So no questions, and thank you very much. Yeah.